There is a saying in English, let bygones be bygones. That is, what is past is past. It is no use crying over spilt milk. This is definitely a very pithy maxim, but there is one branch of science that regularly flouts it, and that is statistics. Instead of looking at the future, they all the time look at the past. So why is it that statisticians look at past data, where instead they should spend time looking at future data? Because whatever is past is already past. As statistics is present all throughout the other branches of science as well, so in every branch of science we find scientists spending a lot of time trying to analyze past data instead of working with future data as they should, if they follow the maxim that let bygones be bygones. Now there is good reason why they do so. It is because this past data and future data, these are connected. These are connected by the underlying process. The same process which is going to give rise to the future data has given rise to the past data. So by studying the past data, we understand the process, which indirectly helps us to understand the behavior of the future data. This is very much like a student studying past year's papers before an exam. What the student is actually interested in is the question paper that he is going to face in the coming exam. But the belief is that the same pattern of questions is going to repeat. So this pattern, the same syllabus, that constitutes the process here. So looking at the past year's papers helps him to get a better idea of the process, which will help him to prepare for the coming question paper. This becomes all the more apparent when there is a syllabus change. The moment there is a syllabus change, this process gets disrupted. The old process and the new process are now different, and immediately students lose interest in studying past year's papers, because this pattern is not going to repeat in the next exam. So it is this unifying fact that both the past data and the future data are connected by a common underlying process. It is this fact that justifies looking at past data. So, when we are having some statistical method, in order to understand whether that method is really good or bad, we should always make sure that it performs well for future data. Now, when we think about a statistical method, we generally think of it as something which takes past data as its input and it produces some inference as its output. So, it is just like a function that maps past data to some inference, some estimate, confidence interval, whether we accept or reject hypothesis and things like that. Just by looking at this, you cannot say whether it is meaningful or not until you have tried it on future data. Remember, the sole justification of looking at past data comes from the fact that it prepares us for future data. So once someone gives us any such method, we must make sure that we spend some time validating it. Now, what is meant by this validation? The validation, of course, takes as one of its input the particular inference that we have, whatever we got out of this statistical method, but that is not enough. We must compare it against future data. So, based on the future data, how this method, the inference obtained from this method performs on the future data, we can say whether this method is good or bad. We can give it a performance score, howsoever we do it, but we have to take into account future data. That is how any method should be validated. Now, if this looks complicated, a simple analogy might help you to remember it. Think of it as a student. So, the statistical method here is like a student, and the student is preparing for an exam. In order to prepare for the exam, the student uses lots of worked out examples. They constitute your past data, things that have been worked out. Now, after practicing all these things, the student learns something, that knowledge, that abstract knowledge that sits inside his brain, that constitutes the inference. But just because a student has studied a lot and claims to have learned a lot, does not mean the student is really good. For that, we need an exam. The validation is the exam, where we put in front of him fresh questions. That's our future data. This must be similar but not same as the questions or the worked out examples that he used for preparation. Based on that, we will see, well, this is what you already know. These are some fresh questions. Let's see how you perform. So how good this performance score is the grade that we give the student in the exam. So that is the complete process. This is true not only for a student preparing for an exam, but also for any statistical method. You can never say a statistical method is good or bad unless and until you have tried it on future data. Just by saying that this is mathematically very impressive is not enough. The need for future data when we want to validate a method is undeniable. But equally undeniable is the fact that obtaining future data is difficult. You have already spent resources to get your past data. You have created your method. Now, future data will come only in the future. So, before you publish your method, if you do not have a way to validate it, then it becomes very difficult. If you wait until the future and then after the future data has been analyzed, then you validate and say, yes, my method was actually very good, that is of not much use. You must be prepared with your method before the future data arrives. And so there is a dilemma. I need future data to validate my method, yet my method should be ready for use before future data arrive. In order to avoid this, in order to solve this dilemma, sometimes people take a drastic step. What they do is they just use that past data as a direct proxy for future data. And that leads to utter chaos. So let us first understand why this is a bad practice using our running example of a student preparing for an examination. So remember, the past data in that example was all the worked out examples that the student used in order to prepare for the exam, and the future data consisted of the fresh question paper. Now, using the past data as a proxy for the future data amounts to asking the very same problem in the final paper. And this will actually encourage cramming. Say, for example, a student has seen in a paper, in a worked out example, that 64 by 16 equals 4. That was given. Now the student, being a stupid one, thought, oh, I understand how it happens. Actually, you have cancelled this 6 with 6 and that's how you obtain 4. Now in the exam, you again ask the same question, what is 64 by 16? And the student uses this argument and again writes the answer 4, and you say, yes, the student knows the answer. This is basically cramming. That is, the student picked up certain pattern which was specific to that example alone. Now, picking up patterns is not a crime. That's how we all learn. Learning is basically recognizing patterns. But we should look at only those patterns which are property of the underlying process and not an accidental pattern which may occur only in one particular data set. Now, whether the student is picking up those accidental patterns or the true patterns, that can be understood only when you ask similar things, like if you now ask the student to divide 25 by 15 and the student cancels up 5 and says answer is 2, then you immediately know that the student has picked up the wrong pattern. But if you ask the same question, in that case, you cannot detect that. So this is basically cramming. I am cramming certain immediate patterns that I can see in the examples without caring about whether the patterns survive for all similar such problems. Now, what we call cramming in case of student is called overfitting in case of statistics. So let's take an example, less frivolous one, that actually occurs when you use the past data as a proxy for fresh data. Suppose you are working in a regression setup and you have a data set like this. So you have these points. You look at them and you say, oh, I can easily see that they are in a straight line. So you can fit a straight line. Now when you fit a straight line, you see that they are not exactly on a straight line. So there is a little deviation here and there. Now someone who is cramming will say, no, there is a little deviation. I will not even allow that. And instead I will fit a high degree polynomial. How many points are there? 1, 2, 3, 4, 5, 6, 7. So I can fit a 6 degree polynomial to it, and the 6 degree polynomial is like this. So which one would you say is the better fit? If you look at only the error, that is, if you are trying to validate this particular fit using these red points, that's the points that you used in order to create this polynomial. If you use these points, then you will see that the error is just 0, because the blue line has been constructed such that it passes exactly through all these points. On the other hand, had you used a straight line, some of the errors will be non-zero. So if you are using past data as a blind proxy for future data, you will say that this blue line is a better fit. But is that a better fit? No, because if you take any other thing, you will see it is just horribly bad. For example, if you try to take a point over here, you see it suddenly swings upward, and here it is going to swing downward. If you take another point here, that is more or less in the same pattern, but this curve does not take that into account. It is picking up even the slight undulations in your data as important signal. So it is mistaking noise for signal. This is an example of overfit that you cannot guard against unless you are using real future data. So we need future data, and we just cannot blindly use our past data as a proxy for future data. So our problem now is, how can we get future data before the future arrives? Well, here is one way of coming out of the problem. It is like this. Suppose we know the underlying process completely. In practice, we do not know it completely, but just for the sake of argument, let's assume that the underlying process which gives rise to the past data as well as the future data, that is known completely. In that case, we can run the process ourselves using a computer in order to get future data. Now, how is that possible? So, when we have a random process, something that provides us with random output, that is a random experiment, completely specified, it is possible to write a computer program to simulate that random experiment. Now, if you are new to this concept, that is very surprising, because we know a computer is what is called a deterministic machine. If you say 2 plus 2, it always responds with 4. If it keeps random thing, then a computer would be completely useless. However, it is possible to program the computer in a way such that it can kind of disguise its deterministic nature and produce random numbers. This is not a very unknown concept. I am sure all of you are already familiar with this concept, that the computer can generate random numbers, and people who feel uncomfortable with the fact that a deterministic machine is producing random things, they like to call it pseudo-random number, to emphasize the fact that they are not exactly random. So if I have a die which can show 1, 2, 3, 4, 5, 6 with equal probabilities, it is possible to write a computer program by which we can recreate that die roll in the computer. Now, it always helps in such a situation to look at an example. So I am going to use the software system R. I think most of you are already familiar with R. So this will be like a quick recapitulation. So here is my R window. There are various ways by which you can use R. You can use R Studio or just raw R. I prefer to use R from my favorite editor, Emacs. So this is the first line. I write data equal to sample C head tail 1000 replace equal to true. So what it says is the following. This is the crucial function that we will be using again and again. It's called the function sample. It draws a simple random sample either with or without replacement that is determined by this particular parameter replace. So if you write replace equal to true, this is simple random sampling with replacement. And here I have written the population. My population consists of only two things, the words head and tails. C is the thing which concatenates a number of quantities into an array. And how many such samples do I want to draw? That is this number 1000. Now, many of you may not be familiar with using equality, just as in any other language. Most people are familiar with this symbol, but equality works just as well, and since it is easier to type, I prefer equality. So let's just execute it. I will execute it, and let's take a quick look at data. In order to see the value stored in a variable, you just write the name of the variable and hit enter, and you see a long list of head, tail, etc. So that is simulating a coin toss. I have not specified the probabilities, which means the probabilities are taken to be 50%, 50%. Now let's try to do some real life application with it. Suppose I am interested in finding out what is my expected profit if I play this gambling game. The gambling game is encoded here. It says if else data equals head. So if data is equal to head, in that case my profit is 100 rupees. So you give me 100 rupees. If that is not the case, else, that is if data equals tail, then I will give you 200 rupees. That is I lose 200 rupees. That gives me my profit. So in one line, I can write the entire if-else. So using the if-else function, which is not a very commonly used function in R. Many people do not know about it. So I will just execute that. Let's take a look at what we have for profit. So it replaces all our heads with 100 and all the tails with minus 200. So it simulates the effect of playing that gambling scheme 1000 times independently in an IID fashion. And I wanted to find out its expectation, that is the average. I am not computing the theoretical expectation here, but by actually playing the game, and that is computed by mean of profit, and that is minus 52.4. So if you do exact computation, you will get I think minus 50, so it goes pretty close. So that is one example by which you can use simulation in order to solve what is effectively a probability problem. Now here is a more statistically oriented one. Suppose I am interested in checking the sampling distribution of X bar when I am drawing a sample of size 100 from random normal, from a normal 0, 1 distribution. So this is how I proceed. I am going to draw it say 10,000 times. So I am going to get 10,000 X bar values, and I need to allocate some computer memory for this. And that is done using this numeric function. Numeric 10,000 means it allocates memory to store 10,000 numeric quantities. So I will do that. And then I enter a loop for I in 1 colon 10,000 means 1, 2, 3, 4, etc. up to 10,000. And in each pass of the loop, I generate using R norm function 100 random numbers from the normal distribution. So we saw sample as one function which generates random numbers from a discrete distribution, from a discrete with finite support, and R norm for standard normal or from other normals. You can specify the mean and standard deviation, which I will see that pretty soon. And this is the sample size. So X is now an array of length 100. And I compute the mean and store it in X bar I, because remember I am going to carry this out 10,000 times. So I runs from 1 to 10,000. So in the ith experiment, this is the X bar that I get. So let's quickly execute them. Well, it just did it in a flash in my laptop, and now I want to have a look at the sampling distribution. Now what better way of getting a visual representation of the distribution than by using histogram? So I will use hist command. So I just type hist X bar, and here I get a histogram which does look like a normal thing. Well, naturally I will be interested in fitting a curve to it, so that I'm just not going to rely on my visual understanding. I want to really overlay the normal density and see it works. And for that I issue this command, curve. D norm stands for normal density, and here I put the standard deviation as 1 over 10. You see I have got sample size 100, so 1 over root 10. And you also see how I specified standard deviation as SD, and I want to plot it from minus 0.4 to 0.4 because that's all that I will need in this case. Let's just try it, and I have written add equal to true. This means you add this curve on top of your existing plot. So I do that, and let's take a look at this. Oops, I do not see any curve at all. And here I suddenly recognize that in my histogram I am showing frequency in the y-axis. So it is not a histogram in the probability sense. So the total area under the curve is much larger than 1. So I have to scale it down, and the way to do it is in the hist command I will specify another parameter called top. The enter form is probability equal to true. I am just shortening it to prob equal to t, and I will issue both the commands once again, and I get a pretty good fit. So the theoretical thing really matches what I have obtained via simulation. So this is just to bolster our faith in simulation. Many people feel very uncomfortable. Is the computer doing the right thing for me? Just by trying out such things, you feel that no, you are not getting any absurd result. Similarly, you may be interested in knowing the standard error of X bar. Ideally, it should be 1 over root n, that is 1/10. I can just compute the standard deviation of all my X bar values. Remember, X bar is an array of 10,000 X bar values. So execute that, and I get something pretty close to our expected value 0.1. So this is how you can actually carry out your simulation.